If dark matter is real, why does nothing we can touch, see, or build detectors forever seem to find it? For nearly a century, we have been told that most of the universe is made of something invisible, something silent, something that does not shine, does not absorb light, does not emit energy we can measure. And yet, without it, the universe should not look the way it does. Galaxies should fly apart. Clusters should unravel. Cosmic structure should never have formed. We call it dark matter. But what if that name hides a deeper problem? What if it isn't matter at all? We know this much. When astronomers observe how galaxies rotate, they see something profoundly unsettling. Stars near the outer edges of galaxies are moving far faster than gravity alone should allow. According to every law we have tested from Newton to Einstein, those galaxies should be unstable. They should stretch, distort, and eventually tear themselves apart into the darkness of space. But they don't. Instead, galaxies remain intact for billions of years, spinning with quiet precision. Something unseen is holding them together, exerting a gravitational pull that does not announce itself in light or radiation. We witness this influence again through gravitational lensing, when light from distant galaxies bends and warps as it passes through regions of space where no visible mass exists. The distortion is subtle but measurable, predictable, repeatable. We see it, too, in the vast cosmic web, the large-scale structure of the universe, where galaxies cluster and align in patterns that cannot form under ordinary matter alone. The mathematics is consistent. The observations agree across independent measurements. The effects repeat no matter where we look. Whatever this presence is, it leaves no shadow we can see. But its gravity is unmistakable. Something is there. But this is where the story begins to fracture. If dark matter is truly made of particles, then by now we should have found some trace of it. For decades, scientists have designed experiments of extraordinary sensitivity buried deep underground to escape cosmic interference, shielded from background radiation, and cooled to temperatures barely above absolute zero. These detectors were built to notice even the faintest whisper of an interaction, and yet the results remain silent. No confirmed signals, no unmistakable collisions, no particles passing cleanly through our instruments and leaving a clear mark behind. The absence is no longer accidental, it is persistent. At the same time, dark matter behaves almost too well. It reveals itself through gravity with remarkable consistency, shaping galaxies and clusters exactly where it must. But it refuses every other known interaction. It does not emit light. It does not absorb it. It does not respond to electromagnetism or the nuclear forces that govern ordinary matter. It acts like matter, but not like anything we have ever touched, measured, or created. And so the question sharpens into something deeper. If dark matter is real, why does it behave less like a substance within physics and more like a shadow cast by physics itself? The first hypothesis is the one most scientists recognize immediately, because it fits naturally within the existing framework of physics. Dark matter, in this view, is made of particles we have not yet discovered, not atoms, not protons or neutrons, but something far more elusive, particles that barely interact with the ordinary matter, forming stars, planets, and ourselves. These particles would pass effortlessly through Earth, through our bodies, through entire galaxies, without leaving a trace we can easily detect. They would reveal themselves only through gravity. Such particles could clump together on cosmic scales, shaping galaxies and anchoring vast clusters of matter, while remaining invisible to light, electromagnetism, and the nuclear forces that govern everything else. If this hypothesis is correct, then dark matter is not mysterious because it is unreal. It is mysterious because our tools are still too blunt to see it. In this picture, the universe is not incomplete. We are Yet this explanation carries a quiet, growing tension. Experiments have become more sensitive, detectors more refined, the search more patient, and still, the silence continues. If these particles fill the universe, moving through everything, everywhere, all the time, why have they left no unambiguous footprint behind? The second hypothesis steps beyond particles and into something far more unsettling. What if dark matter does not exist at all, not because the universe is missing something, but because gravity itself behaves differently on the largest scales? What if the equations we trust work beautifully within our solar system, guiding planets and spacecraft with exquisite precision, yet begin to bend and fail when stretched across entire galaxies and clusters? In this view, nothing invisible is holding galaxies together. There is no hidden substance drifting through space. Instead, gravity quietly changes its rules when distances become immense and accelerations fall to almost nothing. The universe has not been hiding mass from us, it has been revealing gravity's deeper behavior all along. If this is true, then the fault is not in the cosmos, but in our assumptions. Yet the danger here is subtle and profound. A modified theory of gravity must still explain everything else we observe. It must account for black holes collapsing space-time, for gravitational waves rippling across the universe, and for cosmic expansion unfolding over billions of years. So far, no alternative theory succeeds without leaving cracks in the foundation. But the question remains open. The third possibility is the most unsettling of all, because it asks us to let go of the idea that dark matter is a thing in the first place. What if dark matter is not made of particles, and not carried by any force, but is instead a property of space itself? Not substance, but structure. Not matter, but geometry. In this view, space-time may possess hidden features we have not yet learned how to perceive. Subtle curvature, extra dimensions folded beyond our senses, or quantum effects that emerge only across immense cosmic distances. Under this interpretation, galaxies rotate the way they do not because unseen mass surrounds them, but because space behaves differently when stretched across millions of light years. The rules of motion change, not because something has been added, but because the stage itself is more complex than we assumed. Dark matter becomes a name, a placeholder for physics that remains unfinished. And this would not be the first time in science. Atoms were once invisible explanations. Energy was once an abstract bookkeeping tool. Even time dilation was once dismissed as mathematical curiosity. Each time, reality turned out to be far stranger than imagination. One observation could change everything. Not a grand announcement or a sweeping theory, but a single, undeniable signal, the kind that refuses to be ignored. A confirmed detection of a new particle, interacting in a way no known matter ever has. A clear and repeatable deviation in how gravity behaves, measured precisely where our equations say it should not occur. It could arrive as a cosmic signal that simply does not fit, a galaxy rotating wrongly in just the right way, a gravitational lens bending light where no visible mass should exist and no invisible mass can be reasonably placed. Or a faint imprint left in the early universe, subtle, ancient, and unmistakably pointing in one direction. This is how science truly advances. Not through tidy answers, but through fractures in understanding. Through observations that crack open theories we thought were complete. Dark matter sits at the largest of these fractures in modern cosmology, a pressure point where particle physics, gravity, and the structure of space itself collide. Whatever resolves this mystery will not merely add a missing piece. It will change the shape of the picture. If dark matter is real, why does it hide so perfectly? We know that gravity works. We see its influence shaping stars, galaxies, and the motion of light itself. And yet, the universe does not obey gravity in the way we expect it to. On the largest scales, something pulls, bends, and organizes cosmic structures beyond the reach of visible matter alone. To explain this, scientists offer different paths forward: invisible particles drifting silently through space, gravity that subtly changes its behavior across vast distances, or hidden structure woven into space-time itself, deeper geometry that only reveals its effects at cosmic scales. Any one of these ideas could be wrong, or all of them could be incomplete. One observation could change everything. A single signal could collapse decades of debate into clarity. But for now, the question remains unresolved, patient, and vast. At Deep Space Inquiry, we don't rush to close the mystery. We stay with it, because some questions are not meant to be answered quickly. They exist to slow us down, to unsettle our assumptions, to quietly reshape how we think about reality itself. And perhaps the most unsettling truth is this: the universe may not be hiding dark matter from us. It may be waiting for us to learn how to ask the right kind of question.